Welcome to our next roundtable workshop. Our panel leader is Patrick Giraudeau, who will talk about quantitative NMR, other methods than protons. And so before we get started, let me hand things over to John for a welcome.
Thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. And welcome to Ivan Workshop number 27, as was just mentioned. We have a great lineup of speakers today. Very interesting and important subject material, if I may say. And our sponsors, MR Resources and Q1 Instruments, always very happy to bring these meetings to you. And if I may, just a couple of words on our sponsors. MR Resources, of course, been around since 1985 and is your one-stop source for NMR systems, services, and parts. And product lineup includes NMR spectrometer sales and leasing, magnets, consoles, probes, annual service contracts, quenched magnet recovery, and moving and relocation of NMR systems. And I wanted to mention that in this very difficult time of helium delivery and supply, if you're contemplating bringing down any magnets temporarily, contact MR Resources, and they'd certainly be glad to help you out. Eric, if you would give us a word or two on Q1 Instruments, please.
Good afternoon. Q1 is dedicated to developing NMR hardware and software to make routine NMR more accessible to a broad range of scientists and engineers. The company aims to establish new and innovative products for demanding applications across the sciences. Our products consist of complete systems at 400 megahertz with magnets manufactured by Q1. We also offer complete systems with magnets from MR Resources up to 600 megahertz. Our console upgrades in 2 or 3 channels from 300 to 600 megahertz, with the economy console consisting of the Quantum 1 Plus console, preamplifier, workstation, and utilizes the existing magnet probe and shims. This is by far the most economical upgrade in the market. A full upgrade consists of the Quantum 1 Plus console, preamplifier, broadband STM gradient probe, and sample changer for a completely automated system at a price that would surprise you. And our smart tune and match probes for Brooker invariant systems for improved throughput. Q1 probes are fully integrated into the Topspin and vNMRJ platforms. The Q-Link Ethernet-based interface can be installed on a wide range of consoles to fully automate the operation of older NMR systems and add multi-nuclear capability to your dual or quad nucleus spectrometer.
Thank you, Eric, and very good and capable product lineup. Dave, over to you. If you could let us know about upcoming meetings, and especially the big one, day before ENC, which is going to be both live in person and broadcast via Zoom and YouTube. Dave, I don't want to steal any more of your thunder. Okay, I'll turn it over to you.
Well, it's really yours. The yes, so usually Krish, he can't be with us this week, but gives the upcoming meetings. And so I want to certainly mention that our April meeting is in fact the Ivan pre-ENC user meeting, which will be held in Orlando with the ENC, which remains a live event. We still don't have an idea of how many people will be there, but our meeting will be both live in our suite at Orlando, and will be broadcast on Zoom, just like the meeting last year was broadcast with pictures from Asilomar. So we have a mix of speakers from who will either be in Orlando or will be coming in through Zoom. And so it'll start about actually, I've forgotten, about 10 in the morning and go through the afternoon. It'll be a regular user meeting for those who are there with snacks. And hopefully and for everyone online and everyone else, there'll be lots of in between talks, just like last year, there'll be lots of prizes and fun. So we hope, like last year, we hope to make the meeting light and fun with good talks. We have an upcoming meeting for May. Mikhail Raybach from Merck will lead a panel about molecular confirmation via NMR, and that will be May 26th. And at this point, we don't have a meeting for June. We're still working on that. But in July, Jacqueline Thomas from Procter & Gamble will lead a panel about polymer NMR. So those are the upcoming meetings that we have well defined. And certainly there will be more to come as we fill out the rest of the months of the year. So having said that, I will mention that our format is the usual. In a moment, I'll turn things over to Patrick, who will introduce the panel, and we will have talks roughly until the hour, and then open things up for questions and discussion among everyone. So let me hand things over to Patrick to get started.
Thanks a lot, Dave. Hi, everyone. And first, let me thank the IVAN group and organizers for inviting me to lead this panel. I think it's going to be a very interesting discussion. So let me just share my screen. And then before starting, I would also like to warmly acknowledge the two other speakers from this panel, Marco Guerrini and Marco Tessari. I will introduce them in a minute. So I'm just giving a few introductory slides to this discussion, and then we'll move to the three talks. So as you know, quantitative, Proton Nmr is a fantastic quantitative tool, which I think has been discussed in several IVAN panel discussions. And it can do many things, and I like very much this figure from Guido Paoli's and colleagues' paper that summarizes all the kind of sample that you can analyze with quantitative NMR, which can be seen as a universal detector, and the many different applications that can arise from quantitative NMR, as you can see in many different fields. And there are many reasons that probably most of you know why NMR is so popular for quantitative analysis. Now, I'm not going to come back to all these advantages which have been widely described in previous webinars, but I would also like to point out that there are indeed limitations to quantitative NMR. There are things that you cannot do. Well, the first thing is that quantitative NMR, at least 1D NMR, is strongly limited by peak overlap. So peak overlap can occur for different reasons, but especially when you have to deal with the analysis of mixtures. So mixtures can be different kind of sample. It can be very complex biological mixtures, such as biofluids, extracts, stuff like that. But it can also be reacting mixtures, which are not necessarily very complicated in terms of chemical composition, but where the different compounds in the mixture can have very similar structures. For instance, if you consider the monitoring of a chemical reaction, products and reactants can have very similar structures, and then peaks can highly overlap. So on the left here, I took an example of a very strong overlap case because it's the monitoring of an online experiment on a benchtop spectrometer. So of course, in that cases, overlap is even more a problem. So overlap can occur due to the overlap of peaks from mixture components. You can also, you may also need to deal with overlap from solvent peaks, and there can be several if it's reaction monitoring. And of course, combined with that, you have to deal with dynamic range issues. And for all these reasons, different alternatives to quantitative 1D NMR have been developed, and that's what we are going to try and cover through our three talks today. So I will first give an introductory talk about the different methods which are available for the determination of absolute concentration in mixtures with quantitative 2D NMR. Then we will welcome Dr. Marco Guerrini from Ronzoni Institute in Milano. And Marco will describe how he's been applying quantitative 2D NMR to the characterization of complex drugs. So it's very interesting because you're going to have a very practical application of these quantitative 2D NMR methods. And then we'll go one step further with Dr. Marco Tessari, who is in Radboud University in the Netherlands, who will also talk about quantitative 2D NMR, but combined with hyperpolarization and more specifically power hydrogen. And then you will see that not only we can get rid of the overlap problem, but we can also at the same time get rid of the sensitivity limitation of quantitative NMR. So let me start. So each talk is going to last about 20 minutes. After each talk, I will take maybe 2 or 3 questions, not more, and then we'll keep a longer time after the talks for the discussion. So let me start. And what I would like to do in this first talk is to describe different approaches that you can use to obtain quantitative results with 2D NMR. And of course, I like to discuss the advantages and limitations of each approach. And this will be based on developments which have been done by different groups, including ours, in the last 10 years. So this slide is just a very basic reminder of what all of you probably already know. The strength of quantitative NMR is not only that the signal is proportional to concentration, because that is the case for many analytical methods, but the strength of quantitative NMR is that under specific conditions, such as a long recovery delay, this coefficient of proportionality between signal and concentration is going to be the same for all peaks in the spectrum. And that means that in principle, you can quantify multiple molecules in mixtures with a single reference signal, which can be an internal, external, or electronic reference. So with quantitative 1D NMR, you can do direct quantitative analysis with a single reference signal. And that's how you do it. So now this is again a very basic reminder of analytical chemistry definitions, but that will be very useful in my presentation. For absolute quantification, what you first need is a high trueness. And a high trueness in quantitative NMR, in quantitative 1D NMR, is ensured by working in full relaxation conditions with an accurate reference method, such as an internal standard. Of course, generally, you also want a high precision. And precision in quantitative NMR is partly impacted by signal-to-noise ratio. So you may note that a high precision is sufficient for some applications where you want to do only relative quantification or profiling, for instance, in untargeted metabolomics. But for absolute quantification, you want to get both high trueness and high precision. And we'll see how we can try to get that with quantitative 2D NMR. So, well, why considering quantitative 2D NMR? This is a slide I showed in the introduction, so I'm not going to spend more time on it, and I can jump to the next one. So you've got to deal with peak overlap. Well, there are different ways to deal with peak overlap. There is not only quantitative 2D NMR. The first possibility, of course, which is the most obvious, is to do spectral deconvolution or decomposition. And many very robust and efficient algorithms are available to do so. And I also think that some Ivan webinars have been dedicated to that topic. However, from our experience, even the most efficient deconvolution algorithms can fail when peak overlap is too strong. And there are also some problems when line shapes are not ideal or when SNR is not good. Another solution is quantitative C13 NMR, which does work very well, but it requires much longer acquisition times and is more sensitivity limited. Pure shift NMR is also promising, at least in principle, for the separation of complex mixture components, but it also has a low sensitivity, and I think its quantitative potential has not been fully explored yet. And in this context, what we're going to discuss here, it seems relevant to explore the potential of 2D NMR for quantitative analysis. But of course, there are different questions to discuss here, especially about experiment time. I will not discuss it much today, but mainly about the quantitativity of 2D experiments. So this slide is here to illustrate the relevance of 2D NMR for quantitative analysis. First, the fact that 2D NMR, as you can see on the left here, provides a better separation of peaks than 1D NMR due to the additional spectral dispersion along the second dimension. And then there is also the advantage, that there is not one, but many pulse sequences which are available that one can rely on to optimize the compromise between separation of overlap peaks and sensitivity. So the first question to ask is on the quantitative nature of 2D experiments. How do they compare to quantitative 1D NMR? Well, in fact, the formula that I've been showing before is the same, and 2D peak volumes are still proportional to concentration. But the difference is that the coefficient of proportionality is peak specific. And this is because 2D experiments are multi-pulse experiments that make 2D peak volumes modulated by J couplings and relaxation times. And this means that relative quantification or profiling remains possible if the experiment is reproducible. Actually, in Marco Guerrini's talk, you will see a very nice example of relative quantification with classical 2D pulse sequences. But it also means that if you want to do absolute quantitative NMR with a single standard compound, like as you would do in quantitative 1D NMR, then that might not be possible. So what can we do? There are several solutions, actually. The first approach is to do analytical chemistry, actually, and to remember that individual signals are still proportional to the concentration of the corresponding analytes. So this means that each peak response can be calibrated with the corresponding standard, as for instance in chromatography or UV visible spectroscopy. And an important point is that multiple analytes can be calibrated with a single procedure if you design a series of calibration samples that contain all the targeted analytes in non-concentration. The second possibility is to do fancy NMR methods development and to try and design pulse sequences that would be intrinsically quantitative, like quantitative 1D NMR. What I mean here is that in such pulse sequences, which are mainly related to the Hsqc pulse sequence, actually, the coefficient of proportionality between the peak volumes and the concentration would become peak independent, as in 1D NMR. So the idea is to get rid of the dependence of peak volumes on all these factors. And we will come back later on these two different strategies through different examples. The second specificity of 2D NMR is the experiment time, which can actually be quite long due to the need to record many T1 increments to obtain a satisfactory resolution. And this leads to limitations. First, when you have many samples to analyze, there's a problem of being high throughput, but also, of course, when samples evolve in time. And the good news is that there are plenty of solutions to deal with these limitations, and most of them are compatible with the quantitative approaches I will describe later. So I will not specifically describe fast 2D NMR approaches. That could be the topic of another webinar. But let's keep in mind that all what I'm going to present afterwards can be accelerated with some of these methods. Yeah. So now let's focus on the different approaches that I've described before to obtain absolute quantitative results from 2D spectra. So first of all, external calibration and standard additions. These are rather standard procedures in analytical chemistry, so I guess I do not need to detail too much. Calibration consists in recording 2D spectra on a series of calibration mixtures that contain the targeted analytes in non-concentration. On the other hand, standard additions rather consist in spiking your mixtures with known amounts of targeted analytes. So both procedures are quite simple, and they can yield a high trueness and precision that highly depend on the care that the operator brings to the design of calibration mixtures. Actually, that's something we can discuss afterwards. And also, the results are going to depend on the fact that all data should be acquired and processed exactly in the same conditions. The difference between calibration and standard addition is that standard additions are longer to implement because you need to spike each sample where you want to do quantification, while the same series of calibration samples can be used to analyze multiple samples. But there can also be advantages in using standard additions to avoid some matrix effects. That also we can discuss later if you're interested. So the good point with such methods is that you can combine them with any of your favorite pulse sequence and even with any fast 2D method. In our case, we actually ended up in setting up such a workflow to choose the most appropriate pulse sequence, depending on the resolution and sensitivity issues you have to face. And I added here the picture of Estelle Martineau, one of my collaborators who worked a lot on this. And for the analysis of complex mixtures, we actually always end up using one of these 3 pulse sequences: ultra-fast Hsqc, zero quantum filter TOCSY accelerated with NUS, and Hsqc accelerated with non-uniform sampling. And these 3 approaches, which are very different, provide quite a good continuum between speed and sensitivity. So its sensitivity should be located here. So on the left, you have a pulse sequence which is not so sensitive, but is extremely fast. In the middle, a sequence which is quite sensitive and provides a good separation, but is less fast. And on the right, Hsqc is less sensitive, of course, at natural abundance, but provides the best peak separation. So I will briefly go through 2 examples that we can detail later in the discussion if you want. In this one, we used ultra-fast 2D Hsqc to quantify 8 metabolites at the same time in tomato extracts. So you can see here the typical workflow that we used. First, we record 2D spectra on the samples that we want to analyze. So that's, here. Then we prepare a series of calibration samples, here, that contain all the targeted analytes in variable concentrations. And then with these samples, we plot calibration curves that we can use to determine the concentration of our metabolites in extracts by determining 2D peak volumes from unknown samples and then using the calibration curves. However, a drawback is that, of course, to do that, you need commercial standards available. But the good news is that it's high throughput and you can reach quite a high trueness, like typically a few percent. The second example does the same, but with a standard addition approach associated here with a specific pulse sequence, which is an ultra-fast double quantum spectroscopy experiment. In that case, basically, we wanted to quantify taurine in energy drinks, but we could not do it with Hsqc, not even with conventional or ultra-fast Hsqc, because there was a strong overlap between the taurine peaks and the sugar signals. And by using double quantum spectroscopy, we showed that, well, the spectrum was much cleaner, of course, because you basically remove the diagonal contributions without going too much into the details. You filter out these contributions, and we showed that with such approach, we could obtain a very good trueness. So of course, it's less high throughput because you need to spike each sample 4 times, and you still need to have commercial standards, of course. Now I'm moving to the second kind of approaches that consists, so different strategies, the NMR way of getting intrinsically quantitative results with these quantitative 2D NMR methods which have been developed. And the aim of these approaches is to make the coefficient of proportionality between concentration and signal identical for all peaks. And several approaches have been described in the literature, and all of them have been focused on the Hsqc pulse sequence, which has specific properties that can be used to turn these pulse sequences into quantitative experiments. I'm going to give 2 examples here. The first one is this Q2 Hsqc pulse sequence that has been developed by my colleague Jonathan Farjeon. This pulse sequence includes several key elements. It has a perfect inept that refocuses homonuclear proton-proton evolutions. And then you have the variation of inept delays through successive times, through successive scans to average out the JCH modulation. And also a pure shift acquisition is implemented to improve sensitivity. And thanks to this pulse sequence, you can use a simple internal reference as in 1D NMR and obtain a trueness that is around 10%. The reason why it's not better is that the pulse sequence does not compensate for the moment for differences in T2 between the different peaks. So if T2 are similar, that's fine. If T2 are too different, it increases the error. Another drawback of this experiment is that it's quite long. So here is a way to make it faster by accelerating it with different features, such as a variable recycling time, which is some kind of built-in apodization at the acquisition stage, also with non-uniform sampling and spectral aliasing. So I think that now, let me show some application of these methods, which I think is very interesting. We were asked by a collaborator in Canada to quantify these two natural compounds here in herbal extracts. And we did it with this Hsqc method and using DMSO2 as an internal reference. And we compared the results to those obtained by LC-NMR. No, sorry, why did I see? No LC-NMR with UPLC, sorry, no NMR here, using purified samples as standards. And the results are very similar. So that's a good indicator of the performance of quantitative 2D NMR. Now, even more interesting is that one of the reviewers for this paper requested that we also compare the deconvolution of 1D NMR spectra, which we did with one of the best commercially available tools. And that's a case where 1D NMR fails, even with deconvolution, which we could attribute here to the very strong peak overlap that we had here, and also to non-ideal line shapes that made deconvolution not very efficient. And I think this further justifies the need to use 2D NMR in such cases. And just to finish my talk, I wanted to explain the principle of the Hsqc 0 pulse sequence, which is also very interesting. This experiment was suggested, I think, a decade ago by John Markley and co-workers. And that's a very nice idea that consists in recording 3 different Hsqc spectra on each sample that you want to quantify. The first one is a regular Hsqc. In the second one, the whole pulse sequence block is looped twice before the acquisition. And in the third one, the whole pulse sequence block is looped 3 times. And these 3 experiments provide peak volumes that are more and more attenuated under the effect of J couplings and T2s. And now if you plot these 3 peak volumes on a logarithmic scale, you can extrapolate and you can determine the theoretical peak volume that each peak would have on a hypothetical Hsqc with absolutely no evolution delay, called Hsqc 0. And in this Hsqc 0 hypothetical experiments, peak volumes can be used as 1DQ NMR integral and reference to a simple internal standard. And this approach can yield a very good accuracy with no need for commercial standards. Now the drawback is that it's quite long, since you need to record 3 Hsqc spectra for each sample. And the Hsqc 3, the third spectrum, is also not very sensitive since peak volumes are highly attenuated under T2 relaxation. So it can happen that you do not detect any signal on the spectrum here. And that's just a simple example that we did not publish where we used Hsqc 0 to quantify vanillin just to learn how to use the methodology actually. So that's just some concluding remarks. So you have different ways of achieving a quantitative analysis by 2D NMR. You can use analytical chemistry approaches, which are very easy to implement, quite accurate, but the main drawback is that you need commercial standards, like in any other analytical methods actually. And then you can also use specific NMR pulse sequences, which is very good because you don't need commercial standards here. The accuracy is not as good as the other ones for the quantitative Hsqc experiments. The Hsqc 0 is better, but of course these approaches are limited to the Hsqc experiments. So if you are at natural abundance, that can be not very sensitive. So I think there are still many development perspectives here. On the acquisition side, it would be very interesting to have these intrinsically quantitative 2D experiments in a homonuclear version, which I guess is not very easy to design. We can discuss that later. And we also need tools on the processing side. From my experience, so far, we don't have very well standardized automated tools for 2D peak integration. So it's a little bit like everyone is using his own tool. And there are also not many tools for the deconvolution of 2D NMR peaks that could improve the accuracy even better. So just acknowledging here the funding sources, and of course our team in CEISAM lab in Nantes University. So I think I'm done with my talk. So let me stop screen sharing, have a look at the chat. If you have questions, you can put them in the chat. So currently there are no questions. So I guess we can also move maybe to the next talk. Feel free to write your questions at any time in the chat, and then we will come back to them during the discussion, and we will discuss about them. And when we will be at the discussion stage, I mean, you will also be able to directly speak. So maybe we should move to the next talk and then I'll discuss some applications of this. So it's my pleasure to welcome Dr. Marco Guerrini from Ronzoni Institute. And Marco, if you want to please share your screen.
Thank you, Patrick, to invite me here in this webinar. Okay, I'm trying to show some application of 2D NMR, in this case Hsqc, for characterization of complex drugs, so for real pharmaceutical products. First of all, a few words for definition of complex drug. Complex drugs consist in a complex of multitude closely related structure, and the entire multitude of components is the active pharmaceutical ingredient, not only a single molecule. And very often, complex drugs present a structural variability that can be used by the starting material or to the manufacturing process. These are some examples of complex drugs. There are glutaranoids that are a mixture of polypeptides, liposomes, iron carbohydrate colloids, heparin and long molecular weight heparin, and other glycosaminoglycan mixture, but there are other many complex drugs in the commerce. In this talk, I will show you how in our lab we optimize method to characterize heparin and low molecular weight heparin. Few words on heparin structure. Heparin is a polysaccharide in which is constituted by a disaccharidic repeating unit of uronic acid and glucosamine. As you can see in this picture, the uronic acid can be hyaluronic acid or glucuronic acid, and both glucosamine and uronic acid can be differently decorated with sulfate groups, or as glucosamine can be also acetylated. And in the sequences of this polymer chain, there are specific sequences like this pentasaccharide, that is in which this free osulfated glucosamine is characteristic group of this sequence that is responsible of the anticoagulant, the biological properties of these molecules, anticoagulant, due to interaction between this pentasaccharide and antithrombin. The complexity of these molecules can be shown by the number of building blocks for a disaccharide in comparison with protein and DNA. You can see that there are, for a disaccharide, 48 possible combinations. And even though many of them are not present in nature, the number is still very high. So the molecular weight, that obviously is a polymer, so there is a polydispersion, and the complexity makes this the characterization of these molecules quite challenging. Heparin overview: the use of heparin is used prevalently as the anticoagulant in open heart surgery and in kidney dialysis, while the low molecular weight version of heparin is used in the prophylaxis of venous thromboembolism. Heparin is extracted by pig mucosa, intestine of mucosa, and more rarely from beef mucosa. And to have a view of the number of animals necessary to produce 1 kilogram of heparin is 4,000 pig. The global market is quite high. It is now about more than $11 billion. And we have to say that China holds about 60% of the global production. Proton Nmr, you can see here, there are quite very limited, the spectral resolution is quite low, even at high molecular, magnetic fields. You can see the spectra is quite similar. There are differences according to the origin of the heparin, and you can see that especially for bovine mucosa heparin, there are some extra peaks corresponding to the less sulfated sequence that are characteristic of these molecules. As we have seen before by the talk of Patrick, the 2D NMR and especially Hsqc provide a better separation of peaks. And in this slide, you can see the anomeric region of the saccharide chain, which can be distinguished. This tetrasaccharide is a co-linker region that link the polysaccharide chain to the proteoglycan from which the heparin is biosynthesized. The uronic acid in blue, which you can see here, glucuronic acid, hyaluronic acid, and glucosamine that are in black. And you can see that it's possible not to isolate it, to quantify each single monosaccharide according to substitution, but also have information about the sequences because, for instance, the glucosamine linked to glucuronic acid has a different chemical shift of glucosamine linked to hyaluronic acid or hyaluronic acid to sulfate. Okay, this is the other part of the spectrum, which is very useful to determine the sulfation position 6 between these two signals. And what we have done, we use this from quantitative purpose to really compare batch. In fact, as Patrick mentioned before, this proposed analytical method is designed for comparison study and not to determine the absolute concentration of the polysaccharide. And moreover, only atoms having similar NMR properties, so coupling constant, T2 are compared. And the evidence that this can be applied was initially observed by the ratio of the sum of the volume of glucosamine and uronic acid signals that is very close to 1, which is expected for a disaccharide polymer. The repetition unit is disaccharide. So confirming that the response factors of fragment were not very, very different. A particular aspect to apply these methods on real samples, so to compare batch-to-batch variability, is the validation of the method. The validation of the method is normally approached at 2 different phases. One is a pre-validation phase, in which the analytical factors that are, this is a simplified chart, but there are described in this scheme, can be divided in 3 different types: control factor, experimental factor, and noise factor. Control factors are those factors that can be determined a priori and checked before to set up the experiment, like obviously magnetic field, spectral width, 90-degree pulses. These are all parameters that can be decided and be chosen before to run the experiment. Then there are these experimental factors that should be studied experimentally during the development of the method. This experimental factor can be studied in a simple multivariate experiment, first of all, to confirm the robustness of the procedure or to show which factor should be optimized during the experiment. This is especially a relaxation delay, the number of scans, and the sequence also, to see the effect of the sequence on the results. The other factors, noise factors, are factors that are difficult to study, like the more is an operator effect, like phasing of the spectrum, baseline or integration, that should be subject of the test of the phase 2. The real validation, we approach the validation following the ICH, International Conference of Harmonization, in which we apply the same rules with some exceptions. The first is a linearity in accuracy and cannot be investigated in the standard manner, and therefore spiking the component in the matrix with a standard. This is because the fragment of the polymer chain are covalently bound to the heparins. We cannot add a particular monosaccharide and see how this peak grow, the dependence of the intensity of this peak with concentration. What we have done is a repeatability study. We've done with single operator. Intermediate precision, we are running this example with 2 operators and 2 instruments, and the determination of limit of detection and limit of quantification. A few words on LOD and LOQ that is slightly different to what we are usually apply in normal, for example, HPLC analysis. In this case, taking into account that the spiking is not possible, the LOD and LOQ are defined as the content of fragments, or percentage of fragment, showing a signal to noise of 3 and 10 respectively. So the LOD and LOQ depend on the sample concentration, on the number of scans and the spectrometer sensitivity, and is not exactly equal for each residue, because obviously if there is a different line width of different residues, this effect could affect a little bit the determination of LOD. What we observe is that using signals that, in this case, what we are interested is not to quantify the bigger signal, but the minor sequences that are sensitive and are dependent from, related to the biological properties of these molecules. So using these small signals or medium intensity signals, what you observe is that LOD, LOQ, there is a range in change signal by signals, because there are differences in line width, but the difference is not dramatic. I think the better summary of results is in this graph that show the CV of the methods, of the repeatability and intermediate precision. See the fill square are the intermediate precision, the other is repeatability. As you can see, the CV values related to the intermediate precision are always larger than those related to repeatability as expected. And this dotted line indicate that the LOD, the average of LOQ limit of quantification, that was evaluated about 2%. And what we see in this picture is we see that the measured peaks has a CV lower than 2%. The most abundant fragments here present a CV that is lower than 5%. And the residues that has a less than 10%, about 10% of CV, are very close to the LOQ, and practically signal, minor signal that below a limit of quantification has a CV higher than 10%. But most of the peaks has a CV that quite low, that can be used to compare, so is enough to compare batch-to-batch variability. To determine and to verify if this method, the accuracy of this method, what we have done is the comparison between the NMR method with the classical method, that is the enzymatic cleavage, it's a HPLC analysis of enzymatic digested product of the polymer. So we degrade polymer to disaccharides, or di and tetrasaccharides, and then with Hsqc exclusion chromatography, we evaluate the percentage of each building blocks. In this slide, you can see that the comparison between the two methods show a quite good comparability. So if you have two different methods that provide you similar results, this means that both methods are quite accurate. The only difference is the 6-sulfation of glucosamine. And this, we know the reason of that. It is mainly due to the different T2 of the primary alcohol, that when it's sulfated, obviously this group is quite huge, and the sulfation affects a lot of the T2. And so the precision is quite high in both cases, but the accuracy, especially for the NMR, is not good to compare the enzymatic methods. We also try to compare results obtained from inter-laboratory study. Here there are, use a different sample, the same 5 sample of heparin from the same producer, that they use the similar method of purification. 2 other porcine heparin provided from 2 different suppliers, and 2 different heparin originated by different animals, bovine and ovine mucosa heparin. We perform experiment, Hsqc experiment, with different instruments, 500, 600 megahertz, but instrument that keep different probes, so from a normal room temperature broadband probe to cryoprobe, and using also Prodigy that has intermediate sensitivity in broadband and cryoprobe. As you can see, that to obtain the same or similar signal to noise, we have to use different number of scans, and the experimental time varies a lot, from about 3 hours up to overnight experiment in case of 500 with the room temperature probe. These are results, and you can see that all labs found very similar results, and especially distinguish different heparin, because these are the other two producers, and you can see these are only some glucosamine sulfate, some monosaccharide, the characteristic monosaccharide as an example. And if we apply principal component analysis to analyze better this result, what we can see here that each lab, each instrument, characterize heparin in correct way. So the groups of porcine 1, 2, 3, and the two ovine and bovine are grouped in a cluster in a single space. So this means that also different labs can, if we provide a document, I mean, a standard preparation and instruction to measure and to integrate the signals, obtain very, very similar results. These methods are used to compare characteristic also low molecular weight heparin, and this method was accepted by FDA for comparison between the brand compound with the generic compound in the presentation of dossier for the approval of generic products. Obviously, in low molecular weight is a much more complex system because there are some residues that are originated by the cleavage of the polymerization of the chain. Can be used also different class of molecules. This is a pentosane polysulfate. It is a low molecular weight heparin-like compound that is used for treatment of chronic interstitial cystite. And this is there is a product that is produced by sulfation of 4-methyl-glucurose silane derived from German beechwood. And also here there is a lot of heterogeneity because there is not only a regular chain of xylose or sulfated xylose, but there is branches with the glucuronic O-methylated glucuronic acid, and also the synthesis provide other groups like this double bond that is formed on the reducing end. And Hsqc can be used to compare and to assess, to quantify this signal and to compare batch-to-batch comparison. So in conclusion of this presentation, I think the proposed analytical method is suitable to assess the quality of industrial production. And as I just said, for comparison between the generic and biosimilar drug with the RLD products. Or under the validated experimental condition, that means that we try to optimize the time of analysis is about with the 1.5 hour, 3 hours for using cryoprobe, up to 15 hours using room temperature probe. In this case, the limit of quantification was found between 1% and 2%. So I think acceptable for comparison purpose. The composition analysis result obtained by Hsqc and these different methods, the disaccharide analysis, were found to be comparable, so suggesting the accuracy of the method. And the method can be in principle adapted to all types of complex molecules. This is our studies that are moving these techniques to different compounds. I have to acknowledge the people that were involved in this work, so the group of Ronzoni and FDA that collaborate with us in development of this method, and also Brucker Spectroscopy in Francesca Benevelli. And thank you for your attention. And if you have a question.
Thanks a lot, Marco, for this very nice talk. So you can ask a question in the chat. So I see that there's a very interesting discussion that started in the chat, but since it's more related to the talk I gave before, I suggest that we keep it for the long discussion that we will have at the end. I have a specific question for you, Marco. I think that in the past, you've also here you've been showing results obtained with classical Hsqc, where you're doing very interesting relative measurements. And I have in mind that in the past, you've also been evaluating more intrinsically quantitative to DeepL sequences, like I don't know if it was Hsqc0 or QQ-Hsqc, or I don't know. Am I right? And then if it's the case, what is your vision on that? And maybe it would be interesting to know if you are still using them or if you stopped. What is the reason for that?
In the principle, we evaluate different path sequences, also to evaluate, because this experiment were done with classical sensitivity improvement sequences. And we try also classical methods. The problem is the sensitivity, because to apply reapplication of this method, we cannot acquire a spectrum for a while. We need to have a limited time to provide this analysis. The sequences have obviously effects on the ratio between the signals. But as I mentioned before, our interest was to have a precise methods that allowed the comparison, best-to-best comparison. We were quite surprised about the overlapping between the two different methods of the disaccharadic analysis and NMR. Because we try to, there are some also in minor peaks, some differences, and all of these differences can be explained to different factors. As I mentioned, the T2 is one of the bigger effect, because obviously, especially for sensitivity improvement experiments, the time of acquisition, the experiment time, I mean, the acquisition time is quite long, and you have effect of T2 are quite important in this sequence. We would like now to adapt and to try to optimize these sequences. But always we cannot use sequencing. Overnight experiment is not applicable for real analysis, because when you have 10 batches to analyze, you cannot wait weeks to obtain results.
Thanks a lot, Marco. So if you have questions related to Marco's talk, you can also ask them in the chat, and we'll come back to all questions and have a discussion at the end. And in the interest of time, we're going to move to the next talk. So as you've been mentioning, we often have to face sensitivity issues, and you will see how we can solve that with Marco Tessari's talk. So Marco, if you want to share your screen, and the floor is yours.
Thank you, Patrick. Thank you for inviting me. I'm glad I can contribute to this discussion group. So the work we do is basically to try to apply hyperpolarization techniques to the analysis, the NMR analysis of dilute components in complex mixtures. And in the coming 20 minutes, I'll try to present an overview of what we have done, a few examples of the possibilities of hyperpolarization NMR in chemical analysis. So these slides kind of summarizes what you have already discussed in the in your first lecture very clearly. And what you see here is that low micromolar is a kind of limit for routine NMR. Even in this case, where you see is the signal of quinazoline, which is a very sharp singlet, very well resolved, separated from the rest. Well, low micromolar is where you can get. So clearly, next to a lot of positive aspects, positive features of NMR, resolution and sensitivity represent a major limitation. And one way to address this sensitivity issue is represented by nuclear spin hyperpolarization, which is sketched in these slides. So the situation on the left-hand side is what we all know is thermal equilibrium, where means the population difference between these two spin states is very modest, which translates in a low magnetization and relatively low sensitivity. By hyperpolarization, what we do, we create transient situations where the population difference is greatly enhanced and giving rise to large magnetization and signal enhancement by several order of magnitude, 1,000 times or more, depending on the particular technique and nuclear spins that are considered. Now, one of the techniques that we found very interesting in the very beginning was represented by Sabre, which is an acronym for Signal Amplification by Reversible Exchange. And this is a technique based on parahydrogen. The principle of the technique is represented here. So what you need is an iridium catalyst in a solution, in an organic solvent, in the presence of parahydrogen and substrate molecules that can transiently associate to the catalyst. So what happens is that a low magnetic field, what we have is that in this complex, we have a conversion of a spin order of parahydrogen to enhanced magnetization of the nuclear spins of the substrate, in this case, pyridine. And then pyridine dissociate and a new pyridine associate together with parahydrogen. So the process keeps going and we keep accumulating hyperpolarized pyridine in solution. So this works very well at low field. So after like 10, 20 seconds, we can insert the NMR tubes and a magnet and then measure an NMR signal, which is enhanced by hundreds, thousands times or even more. So of course, we're dealing with a technique that is not universally applicable because what we need are molecules that can associate with a catalyst. But over the last 10 years, this process has been demonstrated for very many classes of compounds, and only a few of them are listed here next. And as I said, not only for protons, for all kinds of nuclear spins, it works extremely well. It's a very powerful technique. And before I proceed further, a few words of parahydrogen. How do you get parahydrogen? Now, when we refer to parahydrogen, we mean the antisymmetric spin configuration of molecular hydrogen. Now, at room temperature, what we have, a thermal hydrogen consists of 75% orthohydrogen and 25% of parahydrogen. Anyway, parahydrogen is the lowest energy configuration. And if we cool down hydrogen down to 20 Kelvin, we can basically enrich our hydrogen close to 100%, as shown here on the left and side. So for this, you need to have something like iron oxide, charcoal, magnetic particles that can speed up the transition from ortho to parahydrogen. Once you have enriched your hydrogen with a para isomer, you can bring it to high temperature. In the absence of magnetic particles, you have this metastable condition that can survive for a quite long time, days or even weeks. So you can use then this parahydrogen as an hyperpolarization source. And so here is an example of what we did a few years ago using Sabre. So what we have a mixture here of like 15 different substrates, few hundred micromolar each. And what you see in black is the thermal spectrum consisting of 256 scans. And in red, you see the Sabre spectrum of the same sample acquired with a single scan. And the small insert here shows the signal of one of the ortho signal of nicotinamide, which here was only close to 10 micromolar. And you can compare with the thermal spectrum after 256 scans. So to realize how efficient can hyperpolarization be. Quantification with hyperpolarized spectra is not trivial, and this is something that strongly deviates for thermal equilibrium conditions. So what we use, we can use calibration techniques to quantify analytes in solution. So in this case, what we did was standard addition for nicotinamide, and this is the result, as you can see, which is we found out something pretty close to the within experimental error to the nominal concentration of nicotinamide in solution. An alternative to Sabre is represented by this non-hydrogenative FIP approach. We use exactly the same machinery consisting of an iridium catalyst, an organic solvent, and parahydrogen, but now we operate high field. And when you work at high field, then there is no transfer of polarization from the nuclear spin of parahydrogen to the substrate molecules. And what we have is that the hydrides in this complex can be easily hyperpolarized. And this can be interesting because the chemical shift of the hydride are extremely sensitive to the nature of the other ligand attaching to the iridium catalyst. So we can use, in fact, the hydrides as a probe of the presence of other dilute species in solution. So the advantage for this is, there are actually several advantages. One is that when you measure the hydrides, we have no background because they typically resonate, in this case, around -20 ppm, where there is no background, no other signal resonate from our sample in the area. In addition, this is a process that can be repeated over and over inside the magnet, and allows the acquisition of multi-scans or multidimensional experiments in a way that is very similar to regular NMR. And we apply this approach to different complex mixtures like body fluids and food extract to detect and quantify dilute components. So when you work under dilute conditions, you want to make sure that your catalyst is completely associating with substrates. So what we did then was to add a specific molecule, most of the time is represented here, is this methyl triazole, which has several positive aspects. Well, it has to associate, of course, so to prevent solvent binding, because solvents tend to form very unstable complexes and degrades rapidly the quality of parahydrogen. Because of the high concentration of this compound, all dilute components that associate to the catalyst will form complexes with 1 unit of substrate and 2 units of co-substrate. So they will be present in only one form. So they will be not distributed over very many different complexes, which will reduce the sensitivity and increase the crowding of the spectrum. The two hydrides, because of the asymmetry in the equatorial plane, are chemically non-equivalent, which greatly facilitate the conversion from spin order to magnetization of the hydrides. Further, this molecule has interesting properties because it strongly stabilizes the complexes, which means that you can acquire high resolution spectra and because of the stability of the complex. So the dissociation rates are fairly low. And finally, under the conditions that I represent here, so very dilute substrate in the presence of low millimolar concentration of catalyst and an excess up to 20 times of this molecule, we have conditions in which the concentration of the complex increase linearly with the analyte concentration. So it means that we can expect a linear dependence of the hyperpolarized NMR signal with the analyte concentration, which is something that strongly help if you want to quantify your dilute components. So what you see here is a complex mixture. In this case, it's a solid phase extract of urine and methanol. And this is the area of the spectrum which you would normally analyze using a standard NMR technique. By using this chemosensing approach, what you actually do, you look at hydrides here in an area of the spectrum that's completely empty. And for each analyte that associate to the catalyst, what you have here is a pair of hyperpolarized hydride signals. The signal enhancement because of hyperpolarization can be estimated in the order of several hundreds to thousands. So we can easily access low or sub-micromolar concentration using this technique. So we have applied this on few systems, a few extracts. Some of them are shown here. Most of the times, the molecule we see are heteroaromatic, associating mainly with nitrogen to the iridium catalyst. So here what you see is a detail of the hydride region measured for a solid phase extract of urine. So what you do is simply you have to take this methanolic extract and mix it with a solution of your catalyst inside a quick pressure valve tube with a particular closure that allows you to directly bubble inside the tube parahydrogen. And you do this inside the magnet, and this bubbling occurs under spectrometer control at the beginning of every scan. So basically we replace what is usually is the recovery delay with a bubble period in which we refresh parahydrogen in solution. And after that, the pulse sequence proceed as it would under normal NMR experiments. The only difference is that the hydrides do not start from longitudinal magnetization, but longitudinal spin order. So it's the only small details. But apart from this, then we need simply to, we can pulse and convert this longitudinal spin order into enhanced NMR signal, as shown here. Now, in a solid phase extract of urine, we can expect several hundreds of compounds that are hyperpolarized, and they would all appear in this region of the spectrum. So clearly 1D NMR is not an option if you want to access individual components. And for this, then we use 2D NMR, still homonuclear NMR experiments. So we only look at the hydrides, but it's a zero quantum experiment. So for every complex in solution, what we see is a pair of hydrides. So as you see, depending on the analyte associating to the complex, the chemical shift changes quite a lot. In the vertical axis, what you see is basically the frequency separation of the two hydrides. By this experiment, we can nicely resolve the different components in this mixture, and we can quantify them by using again standard addition. So these two signal boxed in this picture are the hydrides that are formed when nicotinamide associate to the catalyst. And what you can see here is that the concentration in this sample is around 3.5 micromolar with a precision of approximately 10%. So this technique has also been used by others. For instance, the group of Indra Krele in Tallinn has quantitatively monitor nicotine and its metabolite cotinine in the urine of smokers over time. So it's an extremely powerful technique if you want to assess via NMR dilute component in complex mixtures. One of the weak aspects of this technique is that the hydrides do not really carry much structural information. So we cannot, from the position of an hydride, we cannot at this moment understand which particular analytes is associating to the catalyst. So we analyze them by spiking the sample with different components that are expected in the urine in this case, and we could assign a few of them, which are listed here next. So to measure such a spectrum can take something close to 1 hour, but not so much for sensitivity, but because we need to resolve the signals. And as Patrick already mentioned, there are techniques that allow us to speed up this process, fast pulsing and non-uniform sampling. For instance, that's something we use, we try to use for this kind of experiments. So what we see here is the decay of parahydrogen in solution as you measure a number of hydride spectra without refreshing parahydrogen. So you saturate the solution and then you keep recording hydride spectra, and what you see is that parahydrogen decays. But still we can measure quickly without having to rebubble every time, so allows to speed up considerably the acquisition, a number of increments in a 2D. So that's what we see here. We bubble, we acquire some increments, then we bubble again, we acquire different increments in the 2D, and we do it over and over, and then we can reconstruct the 2D at the end. So this is interferogram with all the increments nicely in place. So this allows to speed up considerably the acquisition, and we can do even better. We can simply sample only 50% of this point, or 25%, or 10%, and then reconstruct the spectrum using non-uniform sampling. And that's what we did for an artificial mixture consisting of 20 analytes, each one 10 micromolar. And well, to resolve them, I need half an hour if I do it in a normal way, but then I can do it quick, or can I do it quick and take only 50% or 25 or 10% of the points? And in the fastest case, I can do it in a couple of minutes. And as you see here, you see the correlation of the intensity in the regular spectrum and in the fast spectra, and you see that the technique is quite robust. I want to quickly close referring to recent class of molecules that we've been able to detect with this method. There are amino acid. Amino acid can also interact with this catalyst. They associate in a kind of chelating mode using the carboxyl and the amino group. And interestingly, when they bind, the kinetically stable form is favored form is this one in which these two binding sites are equatorial. And when this happens, then there is no hyperpolarization, because you need to have dissociation in the equatorial plane of the ligands in order to have parahydrogen refreshment. But this doesn't happen because the binding is too strong for amino acid. But luckily, warming up the sample for a few minutes at 50 degrees, then it produces a different conformation where now the amino group is axial and the carboxyl is in the equatorial plane. And this allows the co-substrate that for these complexes is not triazole, but is pyridine, to associate and dissociate, and also then allows parahydrogen to continuously refresh in the complex, which allows the detection of this amino acid mixture at 1 micromolar each in a few seconds. And interestingly, for every amino acid associating to the catalyst, we end up with 2 signals. And by doing this in a mixture of natural amino acid, each one at 1 micromolar, using again the same 2D experiment I showed before, and you can see that they can distribute, and each one of them is easily accessible, can be integrated and quantitatively determined. And we have used this also for directly for urine. So urine is, of course, an aqueous system, and this whole thing doesn't really work very well for in water. So what you have to do is dilute urine a substantial amount of times, like 20 times. Amino acid in urine have concentration ranging from 10 micromolar roughly up to 1 millimolar. So you can dilute them 20 times and still be in a condition to measure them. And in fact, this is by simply adding urine to this organic solution of catalyst and running this experiment, we could easily measure individual amino acid as shown here. Now, by this I stop. I hope I convinced you that hyperpolarization can offer interesting options to detect and quantify very dilute analytes, so down to sub-micromolar concentration, without too much work on the sample preparation side. And with this, I can stop and eventually answer questions.
Thanks a lot, Marco. So same for the previous talk. Feel free to add questions to the chat. We'll come back to them in a minute. Maybe I can start with a question on your talk. For lab, here we have a lot of people who are users of NMR. How difficult or long would it be for a lab who is not familiar with the Sabre methodology to implement it?
Very simple. Very fast. The equipment is can be extremely cheap. Producing per region is really low cost, and normal NMR equipment, so normal spectrometer, are equipped with fast lines that allow you to bubble the per region in your NMR tube during your pass sequence. So you would have really to do very little and what is nice of this approach is that it doesn't feel different from normal NMR. It's not that you're using complicated ideas. When the sample is in, you simply acquire a 2D or 1D experiment, or maybe even a 3D if you like, without particular conditions. I mean, it's really relatively simple.
Thanks a lot. So I suggest that we start the discussion. So I've seen a few questions in the chat, which were so far, well, mainly directed to my talk. So maybe I will start reading the questions, answering, but my two co-panelists can stop me at any time. And people who ask the question can also turn on their camera and speak if my answer is not clear, for instance. So and some questions were also sent directly to me, so I will read them in that case. Maybe I can start with a short question that was asked at the beginning by Dave O'Brien, who was asking if we could use bond selective versions of quantitative Hsqc experiments. So I would say that in principle, yes, but I'm not aware of any paper where it has been developed. Well, of course, I know papers with bond selective Hsqcs. So I guess it would need to be developed. Well, with the external calibration approach, for sure, they can be used directly, as long as the calibration is done with in the same way as the acquisition of the unknown sample. For the intrinsically quantitative methods, that I don't know. I would say in principle, yes, but it needs to be developed. Now, there were different questions about what I've shown at the beginning about how the number I mean, how do we choose a number of increments in the indirect dimension, and how it affects the precision, and why using NUS and so on. So that's a very important question that we've been investigating in the past, and it's a question of compromise, of course, compromise between sensitivity, precision, resolution, experiment time. So what we've been showing in the past is that it's interesting to see that to some extent, the precision of 2D experiment, I'm talking about the repeatability, turns out to be better if the experiment is faster, because you're less affected by the spectrometer instability. So for instance, a COSY with 64 increments can be more repeatable than a COSY with 512 increments. That we've been showing that in the past. Now, of course, if you do that, you lose resolution. So it's a question of choosing the best compromise between the resolution you need and also, of course, the sensitivity and the precision, and also the experiment time. And this is where non-uniform sampling can help, because it's basically going to help you saving time without sacrificing resolution. Now, clearly, coming back to a question which has been asked about that, non-uniform sampling is not magic at all, and it does lead to artifacts. So typically what we are doing is using non-uniform sampling, but not too much. Generally, I would say 50% of non-uniform sampling for homonuclear experiments, maybe 25 for heteronuclear experiments. Not much. Otherwise, you start getting artifacts, and they do affect, of course, the repeatability of experiment. I was asked if they can be removed by processing. Well, not without, I mean, to the best of my knowledge, not without affecting repeatability. So I don't know if that answers the questions from people who were asking about the number of increments or non-uniform sampling, but if you want to speak about that, open your microphone and feel free to do it. Anyone? So I hope I answered the questions. Then I was asked, so it's a question which is not in the chat. I think Thais Mendonça asked me if in quantitative 2D NMR we need or not to use 5 times the longest T1. So it depends. If we are using calibration methods, you can work with partial saturation conditions, provided that the calibration curve and the spectra on the unknown samples are recorded, of course, in the same condition. It's always the same. And that also makes the assumption that the T1 does not change too much with concentration when you go through the calibration range. For my experience, for small molecules, it generally is the case. For big molecules, that may be a little bit more tricky, maybe. What else? A question that I directly received as well was if I could comment. Could you comment if there is an extra care needed in quantitative 2D NMR? Well, I would say you've got more parameters. So of course, there is extra care needed on many different points, but it's always a matter of processing things always the same thing, acquiring things always the same thing, and an extra care in sample prep if you are using calibration samples. For instance, if you use calibration curves, you want to make sure that the pH, the ionic strength are the same in your calibration samples compared to your unknown samples. So they must be as close as possible to the real sample. A way of doing that, for instance, if you want to calibrate, let's say 10 different analytes using a calibration range where the 10 analyte concentration vary simultaneously, is to ensure that the variation of concentration of the standards over the calibration range does not go the same way for all the analytes. So some of them may go increasing and other may go decreasing. And then you may use that to keep an ionic strength constant. So I hope it answers the question. Then I will also ask if you if intrinsically quantitative methods had been used on benchtop NMR. So as far as I know, the answer is no, probably because these methods are heteronuclear methods, and Hsqc on benchtop NMR is not the most sensitive method, of course, especially when dealing with mixtures. But I think there is no problem in using them, but it has not been done yet. So then I also have a very technical question, but before going to that, because it may take some time, does anyone want to speak, ask question? Also Marco, if you want to, I don't know, make comments, ask questions.
Regarding the non-uniform sampling, we also apply non-uniform sampling, as you mentioned, not too much, not more than 50, because even better less than 50, but without any change in precision. This was what we observed. And in terms of increments, yes, it is a problem of resolution. When you have polymer or big molecules, resolution sometimes is really important. Another particular aspect is how you integrate, how you separate peaks that are partially overlapped in 2D. It is another aspect that I don't know if you try different methods of integration. Is another, I think.
Well, actually, that was the other technical question that I got. So what I did is that I was maybe trying to open. I did not prepare any slide for that. Maybe I should have. Just trying to see if I have spectra that I can open in TopSpin, but without preparing it. So it may be not easy. So basically, there are of course different ways to integrate 2D peaks. The simplest method is to do to use the integration tool in commercial software. For instance, in TopSpin, it's rectangles. I think in Mestrenova, it can be different forms. Anyway, and try to define the integration zone. So from my experience, integration zone should be carefully chosen to make sure to take as much as possible of the peak, but not integrating nearby peaks. So it's a matter, it can be quite tricky, and it's a matter of playing with the contour level while designing integration zones. You want to go as low as possible in the peak tail, but if you have a peak nearby that overlaps with it, it's better to take an integration zone which is smaller, even if you don't take the whole peak. It's always better to do that than to integrate also the nearby peak together, especially if it belongs to another compound, of course, because otherwise you will integrate different information in the same region. Then there is another possibility when you've got overlap on 2D peaks, which is to do projections of rows and integrate them as you would do for 1D NMR. And of course, you may have also deconvolution tools for 2D NMR, but so far I've not been very satisfied with them. I don't know if Marco have comments about that.
No, I agree with you regarding the integration, that you have to avoid too large integration area in case of overlapping peaks. We try also to compare Mestre, because Mestre allowed also to use elliptic integration area. Bruker is only a rectangular integration, at least the TopSpin. We see the Mestre, the new one. But we didn't observe a big difference in using both, because the shape of the peaks that we have in polymer seems to be better to integrate with the elliptic area instead rectangular. But we didn't find big differences, I think, in precision using both of them.
I have tried to do the convolution in 2D. I use, because of my background, I use the NMR pipe package, which is mainly meant for protein spectra. I think it's quite nice, but it's not very quick. Let's say it's a lot of work, but it makes a difference. So if you have important data and you have a situation of extensive overlap, the software is very powerful, but not something you can use solve in 5 minutes, let's say.
I have to say that, yeah, please, Marco, please.
No. So for high throughput, I'm not sure it's an option. But
yeah. That's what I was going to say. We also facing this problem, especially when using 2D NMR for untargeted metabolomics, because in that case, we typically have to integrate, I don't know, 500 signals on the same spectrum and apply it to a series of spectra. And one of my PhD students had, it was a real nightmare for her to design all these 500 integration zones. Now what we are trying to do is to develop our own tool under MATLAB, and we have an engineer working on that to try to develop a homemade tool. And I think different people are doing that. But the fact that we need to develop our own tool, which is not ready to be presented yet, mean that there is no consensus solution on that yet, I think. Yeah. So processing is a real bottleneck. I think that there is a question about the Hsqc0 method from Dave O'Brien, who is asking if we can give an approximate ratio of the experiment time for the 3 ones. So basically, what you are looping when you do the Hsqc1, the Hsqc2, and Hsqc3 is just a pulse sequence, but you're not looping the, you're looping all the pulse sequence block between the first 90 and the start of the acquisition. So the 3 of them have basically similar experiment time because they need to be recorded with a long D1, which is approximately the same T1. So that's where the experiment is long. And then I would say that Hsqc1 and Hsqc2 and 3 have basically the same experiment time, but these are long Hsqc experiments because they need to be recorded in full relaxation conditions. So I don't know if it answers your questions. So do we have any further questions? Well, if not, I will thank my 2 co-panelists. Thanks a lot for your very nice talks. I think that was really cool. And I will give the floor back to the organizers. So I think it's Dan speaking.
So I'd like to thank our panelists for their discussions. And I would like to thank the MR Resources for sponsoring these talks and for you people to attend. So with that, I think we can call this meeting closed. Thank you very much.
Thank you.
Thanks a lot.
Thanks.
Bye-bye.
Bye.